Alright, so I'm going to walk you through how to do the relative velocity practice problems. Number one, we have given is a man walking 2.3 meters per second towards the back of a bus. So that's the velocity of A relative to B. But since it's towards the back of the bus, that means it's in the opposite direction of the bus. And the bus, we're told, is traveling 12 meters per second. So VAC then is just the vector sum of VAB which, if right is positive, is to the left 2.3 meters per second, added to vector BC, which is 12 meters per second in the positive direction to the right. Then the vector sum is from the tail of the first vector to the tip of the last vector, which of course is the scalar difference. Is 12 minus 2.3, which is simply 9.7 meters per second, is the speed relative to the ground of the man. Number two, we have an ant running due east across the 1 meter wide moving sidewalk that is moving due north at 2.1 meters per second. If the ant makes it to the other side in 1.4 seconds, what was his velocity relative to the ground? So velocity AB is not given directly, but we know it's going to make it across the 1 meter moving sidewalk in a time of 1.4 seconds. So knowing that velocity is distance divided by time, if he moves across 1 meter of the moving sidewalk in 1.4 seconds, then that means his velocity relative to the moving sidewalk is 0.7 meters per second. And do we have a direction? We know that he's going due east. So at 0 degrees or east. And then it's also given in the problem that the velocity of the moving sidewalk relative to the ground is 2.1 meters per second north, so 2.1 meters per second at 90 degrees. And so again, to find VAC, we just take VAB, which is 0.7 meters per second east, and add it as a vector to 2.1 meters per second at 90 degrees. The vector sum then is from the tail of the first vector to the tip of the last vector. And of course, north and east are perpendicular, and so we just have to do Pythag to get the resultant, which is 2.2 meters per second. And then I need the direction. So VAC is 2.2 meters per second. And the direction I can find from trig, because tan of this angle theta is the opposite 2.1 over the adjacent 0.7. That means that the angle, theta, is 72 degrees by taking the inverse tan of that quotient. And since this vector is in the first quadrant, we just add it to 0 degrees, and we get at 72 degrees. Number 3 says a swimmer who can swim a maximum of 1.4 meters per second in standing water. So that means that 1.4 meters per second is what? Their velocity relative to the water. Now we don't yet know anything about the direction of that velocity, we just know its magnitude. But we know that she's swimming across a river that is flowing 0.8 meters per second south relative to the ground. We also know something about her velocity relative to the ground. We know that she's going straight across the river to the west bank. And so the direction of her velocity relative to the ground is due west, or 180 degrees. So the question is, what direction should she swim in order to make it straight across? In other words, what is the direction of her velocity relative to the river? And in order to find that, we need to think graphically about this thing. And if I take this AV vector, I want to think, which direction does she need to swim in order to get straight across the river? And of course that means she needs to swim upriver. In other words, towards the northwest. As a result, the river is going to carry her 0.8 meters per second due south, allowing her then to travel relative to the ground straight across. Now, it's given in the problem that her velocity relative to the river can be 1.4, so we know the magnitude of that. We know the magnitude of the velocity of the river is 0.8 relative to the ground, and so we can use the Pythagorean theorem to solve for the other side of the triangle, which tells us that she's moving .15 meters per second relative to the shore. And of course, we also can determine the angle here to give us the direction of her velocity relative to the river. We could have used sine from the information given. So sine theta equals 0.8 over 1.4. Therefore, theta equals, using second sine, 35 degrees. And of course, that's in the second quadrant. And since I know the angle that's past the vector towards 180, I'm going to take 180 minus 35 to get the direction, which of course gives me 145 degrees. So the direction she should swim is 145 degrees relative to due east. And the other question is, how long is it going to take her to get across the river? Well, the only distance we're given is in this horizontal direction. The distance relative to the ground straight across the river. And that's given to be 12 meters. And so, in order to find time, I know I'm going to have to use the relationship between distance and velocity, which is velocity is distance divided by time. And when I solve for time, I get distance divided by velocity. But the question is, which distance and which velocity? Well, again, we only have the 12 meters horizontally, or due west, given in the problem. And so, being careful not to mix our components of vectors, we have to choose only the velocity that's in the same direction as that distance, which of course is that horizontal distance, 1.15 meters per second relative to the ground. So when I do that, 12 divided by 1.15, I get it takes her 10.4 seconds to cross the river. Now for problem 4, it's an extension of this same type of situation. It says if the swimmer in number 3 wanted to make it across the river in the least time, A, what should she do? So the key here is understanding that the reason it took her so long to get across the river is not only was she swimming across the river relative to the shore horizontally, but she was also having to swim upriver in order to fight against the current of the river. The only way that she can reach the other side in less time is to take all 1.4 meters per second that she can swim relative to the water and aim it directly across the river. Now, of course, the river is still flowing, and so it will push her south, causing her velocity relative to the shore to be the sum of those two vectors. But since, again, the only distance we have is the distance directly across the river, we have to use this relationship to find the time, which is 12 meters divided by 1.4 meters per second straight across the river. And when she does that, she manages to make it across in 8.6 seconds. Now the second part of the question, B, is or C is where does she end up? And of course, the answer to that lies in where she goes relative to the ground. Because during that 8.6 seconds, the river pushed her 0.8 meters per second south, we have to find the displacement down the river is equal to her velocity in the direction down the river times the time, which her velocity is the velocity of the river, 0.8, and the time is 8.6 seconds. As a result, she ends up going 7 meters, or 6.9 meters, downriver, or south of where she would have landed if she'd gone straight across. And so here we see a classic example of kind of a trade-off problem. Does she want to make it directly across the river, in which case it's going to take her a longer time, or is it worth her aiming straight across so that she ends up downriver, but she can do so in less time? And then finally, part 5, or number 5, is related. It says if the river in number 4 speeds up to 3.2 meters per second, how long will it take her to cross the river then? And of course, the answer to that is it still takes 8.6 seconds. And the reason is simple. If I lengthen this side of the triangle, I end up with her being farther downriver than she wants to be, but because her horizontal velocity didn't change, and the horizontal distance didn't change, the time it takes her to cross the river is still 8.6 seconds. So no matter how fast the river is flowing, it's still going to take her the same amount of time to cross it. It's just the trade-off is going to be she's going to be further downriver when she ends up.